So it's a pleasure for him to tell us about logic in univalent type theory. So I think we're going to hear more refined propositions of types for you.
Thanks, Andy. And unfortunately today I'm not going to talk about surprising things or my work. So there are lots of people, lots of univalent people and lots of hot people here. This talk is not for them, so this talk is for everybody else. And because they already know that. So, so I'm going to elaborate on some points of Steve's talk, and in turn, Flores, after my talk, is going to elaborate on some points of my talk, because we don't have time to do everything here. Yeah.
Well, I think there was a controlling mind behind the program.
So anyways, thank you for the invitation both to be here in the Newton Institute and to give the talk in this workshop. So, okay, so I'm going to say univalent type theory rather than hot, and I'm going to explain this in some slides now. So, but first, before saying what it is, I want to say what it is for. So there are two aims. So the second was discussed by Steve in his talk, and is going to be discussed further by Flores in the following talk. So you want to use some type theory to prove in a different way things you already know from homotopy theory, and so this is called a synthetic approach. So you have a more direct way of defining the objects and also of reasoning about them. So that's homotopy type theory, or hot. But also, and this is what Vladimir and other people are doing in univalent mathematics, is actually do general mathematics, so category theory, algebra, everything, okay? So I think we should make this distinction here. So homotopy type theory is not just for homotopy, it's actually for doing general mathematics, and this is what I want to emphasize here. Not because 2 is not important, but because 2 is going to be emphasized by other people in this workshop. So what is a univalent type theory? Well, it's so some people call it a foundation. I'm scared of that word. So it's a mathematical language, and the key point is that it's invariant under isomorphism, and we can say this by, so if you have a property of an object X, and we have an object isomorphic to X, then this other object also has the same property, okay? Now, this may seem strange if you have a set theoretical mind, but actually this happened at least approximately already since the 70s. So there is this language, Martin-Loef type theory, that Steve mentioned in his talk. It already has this property. Well, not quite what I said in the previous slides, but for example, suppose you consider the type of natural numbers and the product of two copies of natural numbers. What is the right button to press here? It's impossible to find a property that the natural numbers have, but the product doesn't have. And that's because these types are isomorphic. So even though you don't have the univalence axiom in Martin-Loef type theory, it is impossible to actually come up, so write down in this language a property the natural numbers have, but the Cartesian product doesn't, okay? And this is not a theorem of MLTT, it's actually a meta-theorem, and it actually is a consequence of the consistence of the univalence axiom. So this is an application, if you like, of the simplicial set model. Now, in set theory, of course, you can distinguish these types because 0 is in the natural numbers, but it isn't in the product. Well, of course, you have to be a little bit careful because how did you define 0 and how did you define pairs? Okay? Anyway, so it may be accidentally the case that 0 is also in the Cartesian product, right? So, okay, so there are lots of univalence type theories, and the slide there are 3. So one is the one used in Unimath by Vivovsky, Arens, and other people. So it is a very Spartan Martin-Loef type theory, so very minimal. And it has the univalence axiom, which somebody else will precisely define in a future talk, so just to copy what Steve said. But I'm going to say a little bit because it's important to the connection with logic that I want to make. And they have resizing rules. So these are the rules that make some large types, but not all large types into small types. Okay? I'm going to briefly mention that later in more detail. And that's it. So also, as Vladimir said, the consistency of these resizing rules is an open problem. Okay? And what you find in the hot book is something actually in an opposite direction. So you throw everything you can possibly find in Martin-Loef type theories. Even, for example, when you discuss real numbers, you have inductive, recursive, or inductive types, and things like that. And again, there is a univalence axiom. But instead of having resizing rules, you have higher inductive types. For example, the ones mentioned by Steve. And I would say that in practice, the resizing rules and the higher inductive types play the same role, is to be able to define some types that are not definable in Martin-Loef type theory. For example, quotients, but also the circle and things like that. Okay, so you need this to be able to talk about these objects. So Martin-Loef type theory doesn't have quotients, but you can get either with resizing rules or with higher inductive types. Now, the problem with 1 and 2 is that although the theory remains constructive in a certain sense, it's not really constructive in a computational sense, because, as you know, type theory is not designed for axioms. So once you add an axiom, even if it's constructively true, you will still not be able to compute with the axiom. So Thierry Coquand and his collaborators came up, well, firstly, as Steve said, with a model of univalent type theory, which is constructive. And then, inspired by the model, they actually developed a new type theory, reflecting back from the model. And now in this type theory, you can actually prove the univalence axiom. And like Martin-Loef type theory without the extensions, so this theory has good computational properties, so the terms normalize to canonical forms, and so you can actually compute with that. And actually there is an experimental implementation of this which is available on GitHub. It is not advanced as Coq or Agda because, for instance, it doesn't have implicit parameters and things like that, but it's actually a full type theory which extends this Spartan Martin-Loef type theory, and also it has at least some higher inductive types at the moment. People are working to see which kind of higher inductive types are supported by the model, and then possibly extend the type theory with more expressive higher inductive types. So one thing about higher inductive type is that we know many examples, but we don't know what a higher inductive type is as a general concept. Okay, so here, so there are actually many more univalent type theories. For example, there are two implementations in Coq. One is Unimath, and the other is Hot Coq. And then it's not even clear exactly which univalent type theory underlines them because there are differences in the systems. There are other two in Agda. There's another one in Lin. So this is 5, and perhaps are there others that I forgot to mention? And there is, of course, something in the cubical type theory repository. So, okay. So there's lots of univalent type theories around, but I want to actually not commit to any of them in this talk. Okay, so I'm going to consider a Spartan Martin-Loef type theory, perhaps the same as Unimath, but I'm not sure, except for the resizing rules. So I'm going just to have the empty type, the 1-point type, the 2-point type, the natural numbers. I'm going to have finite and infinite Cartesian products, which also give you function spaces. I'm going to have finite and infinite sums. And then I'm going to have one universe of small types, U, and sometimes I will need two universes, and so of extra large types if you want. And then there is this identity type here. Floris is actually going to give you a formal definition with the induction principle and all that, but I'm just going to say things that are not wrong but are not complete either. So this is what I'm going to discuss next, the identity type. So this type collects the ways in which 2 points can be identified. Okay. Now, if you think of something like the natural numbers, actually it is definable in already without the identity type. So you just say, you do it by induction. You say 0 and 0 is the 1-point type, so there's only one way in which 0 can be equal to 0. There is no way in which 0 can be equal to a successor. And then in the induction step, you do it like that. Okay, so in this example, the identity type is always a sub-singleton. But if you define the type of groups, which I'm going to write down soon, then you ask whether two groups are equal in this type. In MLTT, it will be an independent question of how many elements this identity type has. It will sometimes have at least one, and then depending on which extra axioms you add in one direction or another direction, maybe there is just one, or maybe there are lots. Okay, so this is what the univalence axiom decides. So the reason the univalence axiom is possible is that actually the identity type is fairly under-specified in Martin-Loef type theory. Okay, so sometimes I'm going to write equals notation for the identity type, but one has to be careful because sometimes the equality sign gives you the impression that this can be either true or false, or to be more precise, a sub-singleton. Okay, and I'm going to write a triple bar for definitions. Okay, so discuss the identity type already, and now I want to discuss the universe a little bit. So there are many uses of the universe. So one is to define type families as functions. So when do you want to do that? Well, actually, this is exactly what we did in the previous slide. So we define a function from the Cartesian product of n times n to the universe. And we define this by induction on natural numbers. So a function from the natural numbers to the universe. And this is exactly what we did. So if you didn't have a universe, you wouldn't be able to do that. But also, you use this to define types, such as the type of groups. For example, you say that a group is a type. Well, I maybe should subscript here. A group in that universe is a type. Actually, we are going to say that it's a set. So let's discuss this again that was discussed yesterday by Vladimir and today by Steve. So what is a set? Well, an example of a set is the natural numbers, because it means that there's at most one way in which 2 points can be equal. So that's what the set is. And so why do we need this? Well, firstly, to reflect actual mathematics. So groups are sets. But also, so here we are writing an equation for the group operation. Now, if there were many ways in which these two things can be equal, so which one do we mean here? So maybe you would need some coherence laws or something like that. Okay? So use the universe to say that the type of groups, an element of it is a set with a binary operation, a neutral element, and then you write down the equations. Okay, so that's the second use of the universe. And then you can define the type of categories, topological spaces, or whatever you want, and this is something Vladimir discussed yesterday, of some category theory he's doing in Unimath, and so you do things like that. Now, I haven't told you what the univalence axiom is, but one consequence will be that for this type, if you take two elements of this type, then the identity type actually is going to consist precisely of the group isomorphisms. Okay, that's a theorem. It's a consequence of univalence. So, as I said, the identity type is fairly under-specified, but in this particular case, it decides the identity type to consist precisely of the group isomorphisms. Okay, sometimes people say univalence means isomorphic types are equal. Well, that's not something sensible to say, in my opinion, because you're not talking about equality, you're talking about the identity type. And what the univalence axiom is doing is to decide what the identity type is, which was actually left undecided by the rules of the original Martin-Loef type theory. Okay, so now the talk of this talk is logic in univalence type theory. So I want to discuss how you do logic in univalent type theory as opposed to Martin-Loef type theory. So I'm going to remind you again of something Steve said in his talk. So Curry-Howard logic. I'm not going to call it the Curry-Howard isomorphism, because for there to be an isomorphism we need two things, and I'm going to have only one thing here. So, and univalent logic is almost like Curry-Howard logic, but the difference is that rather than taking all propositions as types, we take only the subsingleton types as propositions, and this is exactly as in topos logic, at least in the syntax of the language. Of course, in the models, it's a little bit different, because a proposition is a type such that if it's inhabited, then it is contractible. But syntactically, at least, it works very much like in topos logic. And both are constructive by default, except that you may lose a computational content that then we want to regain later with cubical type theory. And also, they both are consistent with classical logic, so you can postulate excluded middle and choice, of course, and you want to be able to compute, but you won't be able to say false things either. Okay? Okay, so let's look quickly at this again. So just to quickly have this in your mind. So conjunction is interpreted as product, binary product in Curry-Howard logic. So a proof of the conjunction A and B is a proof of A and the proof of B, as Steve said. A proof of A or B is either a proof of A or a proof of B. And the proof of an implication is a function that transforms proofs of the premise into proof of the conclusion. And the negation is just a particular case of implication in the usual way. Now, universal quantification is again like implication, so but except that the premise is not a proposition but an element of a type, at least morally speaking. So a proof for all x, A of x is a function that given any x produces the proof of A of x. And then more interestingly, a proof of an existence gives you a witness, and then a proof of the witness satisfies the predicate A. Okay, so that's how it is like. So and then, as Steve said, Martin-Loef extended this correspondence by adding the identity type. And so here's an example. So you want to say there are infinitely many prime numbers. So now we don't have a proof of that in the usual sense of of first order logic, we actually write down a function. So we write a function that picks an n, given an n, gives you a p, and then a pair with a witness that p is bigger than n, and also a witness that p is prime. So if you write this in Agda, for instance, this will look actually like a functional program. So you write a definition of a function f, and then you just write some code that has these types. And so the type n bigger than p can be defined in zillions of ways. For example, we can do it by induction, like we did the definition of the identity type, or we can say that n is bigger than p if we can find a k such that p plus k plus 1 is equal, and so on. And then you can just as easily define is prime and things like that. And you can do a lot of mathematics like this. So there are some problems, though. When you try to do more advanced things, and for example, you need quotients, then you don't have quotients. There are no quotients in Martin-Loef type theory, so you get into trouble. Then one solution that most people would know here is to use so-called setoids. So you equip a type with an equivalence relation, and then you don't quotient by it, but you carry around this equivalence relation in all your code and your functions, and you make sure your functions respect this equivalence relation, and this leads to the so-called setoid hell trademark. So of the okay, so this can be done, and people do it. And okay, so univalence and higher inductive types are going to give you these things, the quotients. It also is going to give you function extensionality. I haven't told you yet what univalence is, not even approximately, but I'm going to need a consequence of it for the moment. So it says that if you have two functions, f and g, and they are pointwise equal, then they are actually equal. And you don't have this in Martin-Loef type theory, and for the moment I'm going to assume it, and later it's going to be a consequence of univalence. Okay, so I'm going to introduce a new terminology in this talk, and I apologize for that. So this, I'm going to call this, sometimes I'm going to call them univalent propositions. Vladimir used to call them H propositions, and H is for homotopy. And in the hot book, they are called mere propositions, but I think this is too derogatory for such an important notion. So I don't approve of that. This definition is different from the one that Steve wrote in his slide, but is equivalent. So say the proposition is a type, so a type X is a proposition if any two of its elements are equal. And then we also say it's a subsingleton sometimes. And now you can prove using function extensionality that B in a proposition is itself a proposition. And also in this case, all the equalities between the points of the propositions will collapse themselves to subsingletons all the way up in the H-level hierarchy. Yeah, and also I'm going to use in the following slides, if you have function extensionality, any two maps into the same proposition are equal. Okay? So here's an example of a non-trivial proposition. So I claim that there exists a number n which is prime, and it's the difference of two squares of primes. Now, this is a proposition because there is actually one such number exactly, and it's 5. Any proof that you can come up with of this in the system will have to actually give you 5 either directly or indirectly. Okay? So the main point here is that propositions are not proof irrelevant at all. Okay? In fact, the univalence type is a proposition. And this works actually in a funny way. So how do you prove something is a proposition? You pick two hypothetical elements of the type. So you pick two witnesses of a univalence, and now the first thing you do is you prove function extensionality using one of the witnesses, doesn't matter which. And then you start actually developing a lot of lab type theory with these hypothetical elements of univalence, and then finally using this function extensionality you show that these two things are equal. Okay, that's an interesting proof, but I don't have time to discuss it further. But also for my claim to be true and not a lie, I need something else. I need propositional extensionality. So if I have two propositions and one implies the other, actually they are equal. So that's called propositional extensionality, and it follows from univalence, and it's needed to account for this second component. So this is a proposition, this is a proposition, and there is a theorem saying that the product of two propositions is a proposition, but now any two proofs or witnesses of this type here, or elements of this type, will have to have 5 in the first component. But in order to prove that the second components are equal, we need proposition extensionality. So that's needed. And this follows from univalence as well. Actually, yeah, I'm going to mention this later. So here's a subtler example, and this is an example that puzzled people in the 80s and the 90s. So, so this type doesn't need to be a subsingleton, although in the 90s people didn't know that. They were still wondering about that. Until Martin Hoffman and Thomas Streicher produced the groupoid model precisely to settle this question. They could still prove that this type is always a subsingle. In fact, it's a singleton. So this type has exactly one element. And this is provable in the original Martin-Loef type theory. However, yeah, as I said above, so you can prove that this type is a singleton. And one way to say singleton or contractible is that there is a point in the type such that all the elements are equal to that point. So you can prove that, but you cannot prove this. Okay? It's a little bit mysterious, and so here's an example in the models that Steve was talking about. So take us a disk, remove a hole, so make a hole in the middle, take 2 points and 2 paths, one this way, this way. There's no way to continuously deform this path to that path because there's a hole in the middle. But if you can move 1 point in the sigma type there, that's x. So if you can move 1 point, then you can go around the circle, and then you can deform one path to the other. Okay, so and the proof actually, when you do the proof of this, actually it looks very much like that. So this disk gives the example illustrating why this holds and illustrating why you cannot prove that. So a subtler example, and this is a crucial example, is the notion of isomorphism. And actually, this comes precisely because of this sort of phenomena in this slide. So if you define isomorphism in the usual way, so that the function has that f has a function that is both a left and a right inverse. So this type doesn't need to be a proposition. So if you try to prove this in Martin-Loef type theory, you won't succeed. But also you won't succeed to prove the negation. So this is an undecided statement in Martin-Loef type theory. But once you add things like univalence and enough other things, you can actually give an example of a type x where this will not be or a function f where this will not be a proposition. So there are several ways to fix that. In the hot book, 3 of them at least are discussed. The original one by Vladimir Vevovsky is the one in item 2 here. So what you say is that f is an equivalence if the inverse image of every point is a singleton. Now, being a singleton is a proposition, And you can prove that the product of propositions is again a proposition using function extensionality, and then you get that this is a proposition. So this can actually, so although the first one you cannot prove to be you cannot be proved to be or not to be a proposition, in Martin-Loef type theory with only function extensionality, you can prove that this is always a proposition. And the underlying idea is the proof of this theorem here. So this is actually saying that the identity function is an equivalence, right? So this is what this is saying, according to the definition of the following slide. And something that Vladimir also mentioned yesterday, so these two types are related. So being an equivalence implies being an isomorphism by taking suitable projections to build the function g. And there is a clever way that Vladimir called the Grad's lemma yesterday, which, given this data, it actually produces what is needed to show that. So you fix the function. And so if you go up and then down, you get the same thing back. But if you go, let's say, up, down, up, you get another element of this type. Okay, and then this is going to be an idempotent, so that is a sort of fixing a problematic type here, which is not an identity to, which is not a proposition, so that it is. Okay, so now let's formulate a univalence, even though I haven't told you what the identity type is, but never mind. So then you define a new type here, the type of equivalences. So the type of functions which are equivalences. And there are many ways to say the univalence axiom. You will hear from them, I suppose, in other talks later. I choose one which has the advantage that it doesn't need a lot of definitions to be formulated. So I say the univalence axiom for the universe U says that the type of types equivalent to X is a singleton or contractible in this definition, in the sense I gave here. Okay, so that's not the original formulation, but it works. So as I said before, you can show that this type is a proposition in pure Martin-Loef type theory before you postulate it. So you just prove that this type is a proposition. And it is consistent with Martin-Loef type theory, and this is by the simplicial set model, and now also in the cubical model with a constructive proof. And then the consequence is what I said in the first slide. So if you have two equivalent types, and one satisfies a property, then so does the other. So now this is not a meta-theoretical fact. So now this is a fact that you can prove from univalence. And this is what justifies to say what I didn't approve of, to saying that univalence says that isomorphic types are equal. So in a way, actually, you can say that, because isomorphic implies equivalent, and equivalence gives you Leibniz principle. So that's the definition of equality. Two things are equal if they satisfy the same properties. So in a way, actually, univalence does say that isomorphism imply equality. But I think this is
it implies it.
Yeah.
Univalence implies it.
No, sorry. In univalence implies that isomorphism is equality. Sorry, I'm speaking faster than I can hear myself. Yeah, so univalence implies that isomorphic types are equal in the sense that they satisfy the same properties. Okay, but notice. Okay, so I have several remarks to make here. Notice that if you replace this target U by the type of propositions, this is not enough to characterize equality. That will be the true Leibniz principle. And this is not enough to characterize equality. We'll come back to this in a moment. But the important thing is the red theorem. So you can actually prove that if you define univalence using isomorphism rather than equivalence, then actually in Martin-Loef type theory you can show that this univalence axiom is false. You can actually prove it. You need some other things, so I think if you have two universes, that's enough to do that. You use these universes to construct a large type like the circle using torsors, and then you use this to and univalent and fake univalence to prove this. So why is that? Well, in a way, so intuitively. So we said that the Martin-Loef identity type is under-specified. So we say that some things are there, but we don't say what is not. And so as it happens, there is enough room in the identity type to put all equivalences inside it, and this is what univalence does, but there isn't enough room to put all the isomorphisms. There are too many isomorphisms in a way, right? So that's a way to put it. So that's why it is important to consider the notion of univalent propositions. In the very formulation of univalence itself, you need this refined notion of propositions being sub-singletons and not arbitrary types, otherwise things don't work. So there are some logical consequences of univalence. We mentioned function and propositional extensionality, okay? And I'm not going to explain this in detail, but if you stare hard enough to the univalence axiom, you can actually see that it's an extensionality axiom. Really, this is what it is, an extensionality appropriate for type theory rather than set theory. I wish I had time to discuss this. So here's another example of when Curry-Howard doesn't quite work. Try to define the image of a function. Okay, so we do it the usual way. So the image of f is the type of y's for which there exists an x that maps to y. Now the problem with this is that you can prove that the image of x is always isomorphic to x. In particular, the image of the unique map from the Booleans to the one-point type is isomorphic to the Booleans. Whoops, right? This is not what you would like to have, okay? And in fact, this is an interesting exercise. So how do you do this? Well, if I have a point of x, then I apply the function get a y. I already have x, so I put it here. And here we have that f of x equals to f of x. So this is how you go from down to up. How do you go down? Well, you just project this x. And you can show that these maps are mutually inverse. And yeah, so that's it. So that's not the right definition. So what you should say instead, of course, oh, I'm going to skip some slides. Oh, I cannot. It's impossible to do that. So you have to wait to see what I can do. So we need a way to collapse all the points of a type to a single type. There are many variations of this theme in type theories, such as New Pearl. So this is called squashing. But one has to be careful because there are several slightly different notions of squashing, and which have different mathematical properties. So here we want this one. So we want the universal solution to the problem of mapping x into some proposition. So this means it's in a way the smallest proposition. So if you can map x to another proposition, then you can actually map this one to p. So that's the smallest proposition x maps into. Okay, so that's the idea. So there are several ways to extend Martin-Loef type theory with that. One is to use resizing, and the other is to use and function extensionality, so you need both. And the other is to postulate it as a higher inductive type. None of them is very satisfactory because in ignoring the uncertainty about the consistency of resizing, we need function extensionality, which destroys computational content and so on, and the higher inductive types also we don't know how to compute with them in Martin-Loef type theory, and although we know how to compute with them in cubical type theory. Okay, so this is how people did things originally. I'm going to actually not construct it in this talk in any way. We are just going to use this universal property. So we assume that it exists and that it has this property. Although I should mention that for a large collection of types, you can actually define manually the truncation. For instance, if you have a point of the type, you can say, oh, the truncation is just the one-point type. Or if you know it's empty, then it's truncated. And there are many other classes of types for which we can do this, even if we don't know whether the type is empty or not. Okay, so now this relates to Steve's talk, but it relates with now this is a different impredicativity. This is not Steve's impredicativity, so it's just maybe it's the wrong word to use, but it's a tempting word to use. So it doesn't matter how you define this concretely. Using the universal property, you can show that this type is logically equivalent to this impredicative encoding of the truncation. And this, in fact, was the original definition by Vladimir Vevovsky in his implementation of univalent mathematics, and I think they still use that. And this is why they need the resizing axiom, because if you do this in Martin-Loef type theory, you start with a type in some universe, and this results with a type in the next universe. So it's impredicative in this sense, not in the sense of Steve, that who could do funny quantifications. We are not doing that. Yeah. So, okay. So, moreover, this type is a proposition if you have function extensionality, and so this is why Vladimir Vevovsky uses resizing and function extensionality to get that. Okay. So now, what is our logic? Our logic is going to be exactly like Curry-Howard logic, but we are going to truncate disjunction and existence. Okay? And actually, this turns out to give the same disjunction and existence as in topos logic. Although these types are truncated, they satisfy the disjunction and existence properties in the cubical type theory. So let me explain what this means and how it works. So if you have a term in the empty context, so a term with no free variables, which is, let's say, a disjunction, and then you have a proof of this, then you can actually show that this proof must have been either a proof of A or must have been a proof of B. So how do you do that? You prove that the cubical type theory has the canonicity property, so every term reduces to a canonical form, and then the canonical forms of the truncated type are just the inclusions in the triangle. So the canonical forms are given by applying the truncation to an element of X. Okay, so the introduction rule. And so that's how you prove it, and the same for the existence property. So the canonical form has to be a truncation of something, but the something is a sigma, so by canonicity it has to be a pair, and so you get the witness like this. Okay? So that's how it works. So now this is how we define the image, and now this behaves as it should. So we again use sigma twice. The first one is not truncated because we are using sigma to construct a type of some things, so type of y's, and then here we need a property. So why we can give an intuitive intuition of why we need a property and not an arbitrary type here. So because we need to put each y only once in this set. And now if this is not, the thing inside the truncation is an arbitrary type with several elements, so several x's mapping to y, so you put each y once for each x, right? So this is what is happening, so you want to put them only once. That's the intuition. And so now you can prove that this univalent logic actually behaves exactly like higher order logic. So this is what Steve said in his talk. There's nothing here to worry about. Now the disjunction, so how does that work? Well, that's the truncation of plus, but the truncation unfolds to that in predicative definition, and now just apply in the usual rules of type theory, you get these rules. So existential quantifier, exactly like in higher order intuitionistic logic. And if you try to do this Leibniz principle for equality, you actually don't get equality. So this would be, that's Leibniz definition of equality. When you have propositions, what you actually get is the truncation of equality. Okay? So maybe we should say in univalence logic, the equality is truncated equality, but that's not correct. So it's a kind of an art that you learn in the hard way sometimes when you do mathematics in univalent type theory, to figure out whether you should truncate, when you should truncate, and when you should not truncate. And I don't think there is a recipe for that at the moment, but there are some intuitions that people develop, and at some point it becomes easier. So in reality, you don't replace Curry-Howard logic by univalent logic. This is an idealization for this talk. In reality, you mix things as appropriate. So let's, because we're talking about logic, let's discuss briefly excluded middle. So that's how people say excluded middle in Martin-Loef type theory. But actually, it's not excluded middle because it says for every type, provided it is non-empty, you can find a point of the type. So that's actually a global choice. You can prove that if you have this formulation of excluded middle here, actually all types are sets. So you don't want this excluded middle for univalent type theory unless you only want to work with sets. And moreover, if you have enough universes, then it's actually false in the presence of univalence. So what I'm not going to discuss all of them because I want to save some time for questions. So of course the correct way of saying excluded middle is in either of the two usual ways, but restricted to propositions. And this now is consistent. It holds in the simplicial set model if you assume classical logic, which you have because it's impossible to define the simplicial set model with classical logic, as far as we know. And in this case, the truncation actually can be defined by double negation. So if you have excluded middle, the truncation is double negation. And actually, you can prove, I didn't write this in the slide, but you can prove that if the truncation is double negation, then excluded middle holds. You can also prove that. But, yeah, so this is something that people repeat and again, even though it has been discussed zillions of times in the homotopy type theory mailing list. So this truncation does not erase computational content. In fact, if you look at the implementation of the truncation in the cubical type theory, the witness is there all the time. And then the example is this. So if you have any function from natural numbers, if you know that there is a root of this function, you can actually find it. Okay? So I'm running out of time, but maybe I have enough time to sketch the proof of this. So how do you do that? Well, the type inside the truncations brackets is not a proposition because there may be several roots of f. But if you give me an arbitrary element of this type, which is a pair of a number, and prove that it's a root, then you can do bounded search up to n and find another root, which is the minimal one. So now you create the type of minimal roots of f, and that's actually retract of this other type by this construction of finding the minimal root. And this type is a proposition, and so you can eliminate into that type. Right, so let's go back to the triangle. What this is saying is that if you have something inside a truncation, you can only use it if the user is a proposition, right? So it's like a clan of people who have higher privileges. So what we do is we build this proposition from this type of the minimal root. We eliminate there, and now because it's a type which is not truncated, we can just project and we find our root. Okay, we forget it was minimal. So here we forget it was minimal, we just say, okay, we have a new root. Okay, so very often you can exit a truncation, and very often you cannot. Okay, it depends on what you're doing. Finally, well, not finally. So another point is, how do you say unique existence? So people coming from first order logic would usually say it like this: we have one, and given any two, they are equal, right? So that's how usually you formulate unique existence. But if you say this in univalent type theory, unless you're working with sets only, this is going to be a useless statement. So you need something much stronger. You need to say that this type is a singleton. So a unique X is not enough. What you need is a unique pair. Okay, and this is especially the case when you are talking about universal properties, and something that Steve didn't mention, but he mentioned the work in which this actually arises. So when you want to say there is so you want to define, say, product of two types, and say there is a X and Y, so you say there is a unique Z with projection satisfying this and blah. If you say this in this way, you won't get the correct result. You have to say that the type of such things is a singleton or is contractible. Okay. So now choice in Curry-Howard logic is just true, and it's boring. So actually these two types are isomorphic. So if you have a relation, and for every X you can find a Y related to X, then you can define a function that picks the Y related to X, but this is just fiddling around with projections. Now, but however, when you formulate it in univalent logic, actually this implies excluded middle this time. I forgot to write in the slide that actually you get unique choice, which is very useful in practice. So something that, for example, you don't get in the way Koch, the calculus of constructions, handles propositions. So this is very interesting. With this interpretation of univalent logic, you get unique choice as a theorem. Okay, so here is the moral. Sigma is used to express given structure or data in general. For example, we used to define what a group is. Truncated sigma is used to express existence. It's still constructive, okay? But even better, don't truncate. Even better, if you can, define your propositions as types which naturally are proposition. And this is what Vladimir did for the type of equivalences. And as I said already, it is difficult to decide whether you should use arbitrary types or propositions, whether you should truncate or not. We are learning how to do that. But the main point is that we can make this distinction, right? So and this is the main point. So we can make this distinction. But of course, if you start using choice, then you stop saying this distinction. Thank you. I made it all very clear.
Do you think it really is an art rather than a science? It's the way you put that.
I think it's a science in the sense that when you get used to it, you know how to do it, but I don't think anybody has verbalized explicitly how things should be done.
I mean, I suppose there could be several different translations, as it were, in the same way that
yeah, so if you mix Curry-Howard logic with univalent logic, there are several ways you can do things, but usually there is one that is the correct one.
the connection between stuff, properties, structure, and stuff from category theory, which seems to fit quite well.
Yeah, exactly. Yeah, so this is particularly good for doing category theory, as exemplified by the several developments in Unimath and in the hot Coq library and so on.
Are you making a specific terminological proposal that we should start using the term univalent logic to refer to Martin-Loef type theory enriched with truncation bars for all n levels, something like that? Or are you just speaking in a kind of rough way for the purpose of your talk?
I don't know, but I needed it, at least for the purposes of my talk, to talk about this idealized different interpretation of logic.
Yeah.
But I said also that this is a bit idealized because sometimes you actually want to give a witness rather than say there exists one, and sometimes you don't. So it may become a proposal. For the moment, I just needed it for my talk.
I think it's sensible
Okay.
to have a way of distinguishing the topos logic, which just says exists, from the Martin-Loef pure logic, which just says
I give you a
sigma.
witness, yes.
There exists a distinguished or with the sigma, and now we have a way of using a much more expressive, refined language, which has all the kind of in-between variations. You can say there exists in the pure sense. You could say there exists an essentially unique, or you could say
Yeah, something I didn't mention here because I simply don't have time. I did some work with Nikolai Krauss and Thierry Coquin and Thorsten Atterkirch. We actually, there are more degrees of existence.
Yeah.
It's not just sigma and exists.
Right.
Sometimes there are some things in between that are interesting,
Right.
but I don't have time to discuss this now.
Okay, let's thank Martin.